Hello students, welcome back. We went through the tangent line and we saw some pictures that indicate the tangent lines are the best linear approximations. Remember that, and we're going to use some tangent lines here. The theory of tangent line begins from this. The average rate of change is defined as the change of output over the change of input. And if you put it with a graph, then we're going to get something like this. Now, take the second reference point, closer to first. Then we see this kind of visualization. And please note that the sequence of secant lines converging into the tangent line. Even better, you're going to get something like this. Okay. See the convergence? So, we want a tangent line, and tangent line and secant line are very close to each other if we take h value or b minus a value very close to 0. In other words, if the second point, the green point, gets very close to the original point, red point, then the secant line and tangent line become very similar to each other. And that is the essence of the linear approximation, because we're going to do this. This is a slope of secant line, and that is a slope of tangent line, and they're not always the same, of course, but they're going to be approximately equal to each other if B is close to A, if the green point is close enough to the red point. You see? Start from here and then do some algebraic manipulation. Flip denominator over to the other side, then we get this. Alright, one more. Flip this f of a to the other side, and finally we get this. So this is my current function value, and then this is current derivative value, and then b minus a is maybe 1 second later or 2 minutes later. With this computation, we can predict the future function value. That's how we can do linear approximation. Now, if you already know f of b a priori, then you don't have to do this. But in many situations, we have time function. We have variable based upon time. In that case, we know everything about present and past, but nothing about the future. But of course, we can do reasonable prediction. And how do you do that? Here we go, linear approximation. We know the present function value and present derivative value, and then b minus a is a bit of a future time. Let's see, 2 minutes later or 3 minutes later. Multiply accordingly, then you can get the future function value of 2 minutes later or 3 minutes later. Is there a picture associated to it? No, not really. Picture must be coming from the previous cell. Oh, never mind. Okay, let's go to an example problem. Suppose that the speed of a flying bullet is about 700 meters per second right now, and it is about 500 meters away from the target. Estimate the distance to the target a half of a second later. Okay, we are talking about estimation of future value. Okay, so right now 500 meters away from the target, and half a second later it must have got a lot closer. Maybe not hitting the target because bullet is running 700 miles per hour, and then it'll take 1 second to fly 700 miles, and then it is flying, let's see, half a second? Yeah, half a second. So half a second later, it must have flied, what, 350 miles per hour, miles per second, excuse me. 350 meters per second, excuse me, not miles per hour or miles per second. 350 meters per second, and then 500 meters away. So my mental math tells me it's going to be about 150 meters away from the target. Indeed, it turns out that's a computation we're going to end up doing. Here we go. 0.5 seconds later, current position is 500 miles away, 500 meters away. I keep saying this miles, sorry about that. And then the derivative, the slope is 700 meters per second. That's the rate of change. And then half a second later, 0.5 minus 0, current time is 0. Put everything in there and do your computation. Yes, indeed, I have 150. A bit of a warning, this is not a precise computation. This is by linear approximation. The real bullet does not fly straight. It goes down a little bit because it is affected by air resistance and also gravity. And also, the speed does not stay the same. It goes down a little bit as time goes on because of the air resistance. This is just a linear approximation. Okay, here's another problem. Find an approximate value of 4th root of 17 through the linear approximation without calculator. Without calculator, well, people used to do this a lot 40 years ago, but nowadays people use calculators all the time. Still, let's pretend that we are back in 1940s and then let's try to do this without calculator. How do you do that? Well, you can start from 4th root of 16. 4th root of 16 is 2, isn't it? 2 to the 4th power is 16. So that's where we're going to start. And 17 is 16 plus 1. So this is f of 17 and f of 16 plus the derivative times 17 minus 16. That's the linear approximation formula. Remember this? This formula here. So there. And f of 16, well, we know about that. 4th root of 16 is 2. And then 17 minus 16 is 1. And how about the derivative? Well, we can find out. Take the derivative and then plug in x equals to 16. Then you can find that precisely. 1 over 32. Without calculator, you can still do this. You see? 1/2 to the negative, no, 16 to the negative 3/4 power. So 1/4 power is 2 and negative power. So this is 1/2 to the 3rd power. So this is 1/8 and then 1/4 was there before. So we have 1/32. So we can do this computation and it is 65 over 32. And if you use long division to calculate, you're going to get something like this. Well, if you go back to 1920s or even before, like 1800 something, then people used to do this all the time because there was no calculating tool. By the way, this is a computation through Mathematica, so 2.03054 or something, okay, that is better computation using today's calculating tool. And this is through the linear approximation we just talked about. Pretty good, 0.031, 0.031 approximately speaking. So up to 2nd decimal digit, no, up to 3rd decimal digit, I got correct computation. That's amazingly accurate without calculator.